Okay.
Our next speaker is Krystian Gajdzica, who will talk about Bessenrodt-Ono inequalities, please.
Thank you very much for the opportunity to give a talk about my recent research, which is based on my joint work with Bernhard Heim from Cologne, Germany, Markus Neuhauser from Kutaisi, Georgia, and Błażej Żmija, who is also from Kraków, Poland. So today I would like to talk about the problem of the Bessenrodt-Ono inequality, which is related to the theory of partition. So at the beginning, let me repeat the definition of a partition. So by a partition of a non-negative integer n, we mean any sequence of positive integers, lambda 1 and lambda j, whose sum is n. And by the number of all partitions of n is usually denoted, traditionally denoted by p of n. And for instance, we have 7 partitions of 5 corresponding to the following sequences. Actually, over 10 years ago, great research related to searching for properties related to the log behavior of the partition function emerged. It was initiated by the work of DeSalvo and Pak, who proved that the partition function is log concave for all n greater or equal to 26. So by the log concavity property, I mean that a sequence, that sequence is log concave at some point n0 if it fulfills the following inequality at that point. So there is the result of DeSalvo, who actually reproved the theorem from Nicola from 1978. And the work of DeSalvo and Pak initiated a very great research related to searching for similar phenomena for other partition statistics, for instance, the higher order 2 inequalities, the R-log concavity property, or the higher order Laguerre inequalities. Also, there is wide research devoted to the so-called Bessenrodt-Ono inequality. So in 2016, Bessenrodt-Ono proved that the partition function also fulfills the following inequality, which seems to be a little bit weaker than the log concavity property, but it also requires some work to prove it. Especially they used a lemma-type estimation of Radamacher series to prove that fact, but it's also worth pointing out here that there are other proofs of this inequality. There is a combinatorial proof by Professor Al-Nazi, Jajola, and Munagi. Professor Munagi will be also discussing the topic today, so there will be time to get more knowledge about the Bessenrodt-Ono inequality later. Also, here is also worth pointing out that there is a proof by induction due to Bernhard Heim and Markus Neuhauser. But today I would like to actually pass from the discrete problem to the continuous one and consider the analog of the Bessenrodt-Ono inequality for some family of polynomials. So let me present the motivation. So the motivation is the way of calculating partition function. So probably we all know that the partition function could be calculated using an Euler pentagonal number theorem. So the recurrence actually which follows from the Euler pentagonal number theorem, which allows us to calculate the value of P of n quite fast. However, there are also other recurrence relations which are satisfied by the partition function. For instance, there is the result due to Ramanujan from 1918 stating that the partition function of n is equal to 1 over n times the sum over k from 1 to n, sigma of k times P of n minus k, where sigma is the sum of divisors function. So there are a few proofs of that equality. So let me say a few words about the combinatorial one. Namely, let us take a look on the left-hand side of that equality. So here we have n times P of n. So in other words, on the left-hand side we just consider the total sum over all partitions of n. We have exactly P of n partitions of n, and the sum of all partitions for a given partition is n. So the total sum is n times P of n. That's the left-hand side. On the right-hand side, we can take a look on a specific number j, positive integer j, and check and calculate what is the contribution of that j in all of the partitions. So if J is a part of a partition, then we can subtract it from N. So in other words, J occurs at least one time in P of N minus J partitions, but it may occur more times. If it occurs 2 times, then you can subtract J 2 times, and so on. And now we can put it to, okay, so we can now rewrite the sum on the right-hand side, taking, for instance, sigma of J, then we will obtain J times P of N minus J, then later we can put, instead of K 2J, we will obtain, the sum will be 1 plus J plus 2 times J, maybe something else, times P of N minus 2J. We can take J in front of the bracket and we will obtain just the term I wrote at the bottom line. So this is the one proof, but there is also another one using generating functions. In fact, it is more general proof, so let me present it. So we know that the generating function of the partition function takes the following form. Let us take the right-hand side to the power x. If we do that, then on the left-hand side, instead of the partition function, we obtain the family of polynomials, which is called Nekraskov-Okunkov polynomials. And these polynomials satisfy a lot of interesting properties, especially which is clear that Pn of 1 is just the partition function and P of nk is the k-colored partition function. So this is the number of partitions of n where each part can occur in k distinct colors. Moreover, we have the degree of this polynomial Pn is n, the leading coefficient is 1 over n factorial, and moreover, it turns out that we have interesting recurrence relation which follow from the from taking the logarithmic derivative with respect to x and q, and with respect to q and x. Sorry. So if we do that, then we obtain that this family of polynomials satisfy the following recurrence relation, which is very similar to that one from the previous slide. We just need to put x equals 1 and we obtain the recurrence relation for the partition function. But as I mentioned, there is also another recurrence relation for the derivatives of these polynomials, which could be also expressed in terms of that polynomial P of n minus k of x. And now we can ask about the Bessenrodt-Ono inequality for that family of polynomials. But what does it mean? So in the original statement of Bessenrodt-Ono's theorem, we have that P of A times P of B is greater than P of A plus B. And in the case of the polynomization, we have the Heim-Neuhausen-Truga theorem from 2020, stating that this family of polynomials defined in the previous slide satisfies the following inequality for all A and B, such that A plus B is greater than 2 and X is greater than 2. Also, it is here also worth mentioning that we can assume that A and B are just positive integers, but then we need to require that X is greater or equal than 3. It will be more visible later. But now we can consider, so this is just one family of polynomials. So let us do it. Let us repeat the procedure for other family of for other partition statistic. For instance, for the plane partition. So the plane partition is a two-dimensional analog of a partition. Namely, instead of non-increasing sequence, we have the non-increasing arrays in each row and each column. And we can define analogously the plane partition function. For instance, we have 6 plane partitions of 3 that corresponds to the following representations. And once again, we can consider the generating function of the plane partition function. Due to McMahon, we know that it takes the following form. Taking the right-hand side to the power x delivers us once again the family of polynomials Ppn of x. And once again, it turns out that this family of polynomials satisfies very similar properties to that one which was defined for the partition function. So we have that degree is n, the leading coefficient is 1 over n factorial, and we also have this recurrence relations with the difference that instead of sigma of k, here we have sigma 2 of k, which is just the sum of squares of divisors of k. But this is a subtle difference, which is just we just change the sequence here. If we would like to take a look on the Bessenrodt-Ono inequality in that case, we obtain the following. So this is the result of Heim and Neuhausen-Truger from 2023, stating that the plane partition function fulfills the following inequality for all a and b satisfying these conditions. And for the polynomization, we have that if x is at least 5, then we have the Bessenrodt-Ono inequality for polynomials for all positive integers a and b. So we would like to go a step further. So up to this point, we just consider a few very special family of polynomials. So let us generalize the approach a little bit. The first way to do that is to consider any set, or more generally multiset of positive integers, and consider the partitions of n whose parts belong to A. In that case, it's well known that the generating function of the corresponding partition function takes the following form. Once again, repeating the same procedure, we obtain a family of polynomials, Pa of nx, which have very similar properties. There are some differences. Let me explain them soon. So, for instance, we have that the degree is smaller or equal than n. In fact, if one does not belong to the multiset A, then it is strictly smaller than n, usually. So it is not n. But if one is in our set, then we always have degree n. Moreover, the leading coefficient is not usually equal to 1 over n factorial. It is 1 over n factorial if and only if, actually, when one occurs exactly once in the multiset A. And moreover, we once again obtain a very similar recurrence relations, with the difference that the sigma or sigma 2 is replaced by sigma a of k, but now sigma a of k is the sum of those divisors of k that belong to multiset A, and they are counted with multiplicities, so meaning that if in A we have one which occurs there 2 times, then we need to calculate this 1 2 times in the sum. And once again, we can consider the Bessenrodt-Ono inequality for that family of polynomials, and what we are able to obtain is the following. Namely, this is the analog actually for the polynomization of the partition function. That is the result I mentioned before. So here we have this result, and now we consider the multiset, actually the set of positive integers, which is a subset of positive integers, but we require more. We require that one is in our set A. If that is the case, then we can state that this family of polynomials fulfills the Bessenrodt-Ono inequality for all positive integers a and b and x greater or equal than 3. There is an exception, namely if we have that 2 is in our set A, then we have the equality instead of the inequality only for the triple AB of x that corresponds to 1, 1, and 3. That's the only possible case when we can obtain equality for x greater or equal than 3. Similarly, for the generalization of the result for the plane partition function, we were able to deduce the following, namely if A is such a multiset of positive integers that one occurs exactly once in A, and each number j appears at most j times in A, so the border case is just the generalization of the, so this is the plane partition case, because in the case of the plane partitions we have a multiset in which each number j occurs exactly j times in A. This is the result of McMahon, actually the generating function I mentioned before. But here, if that is the case, we have the Bessenrodt-Ono inequality of that kind. But there is once again one exception, namely if we have the situation in which 2 occurs in A two times, exactly two times, then we have the equality for the following triple. But once again, all of these theorems I mentioned are very similar to each other. We just replaced a lot the sequences. We start with sigma, then we replace it by sigma 2, then we replace it by sigma A, and we could fun in this way for a very long time. So maybe let us try to do a little bit more general thing. Let us take any sequence of positive real numbers, which is normalized, meaning that g of 1 is equal to 1. And now, instead of considering generating functions, let us consider the family of polynomials, which is defined recursively by the following formulas. So p0 of g is 1, and p g of n takes the following form. So we can just take instead of g sigma or sigma 2 or sigma a, whatever we like. But we need to remember about this assumption, or we can normalize it by dividing the sequence by the value of g of 1 if it is not 1. Okay, and now it turns out that this family of polynomials also fulfills similar properties as before. The degree is n, the leading coefficient is 1 over n factorial, and we also have the recurrence relation for the derivatives. But now what we would like to have is to have the general result concerning the Bessenrodt-Ono inequality for that family of polynomials. What can be done? Actually, we were able to derive the criterion, which is nested in the following statement. Namely, we have our assumption on the sequence G, and we assume that there is some number x0 such that the following inequalities hold. Namely, we need to require that the family of polynomials associated with the sequence G is greater or equal than the maximum over I between 1 and m of g of m plus I divided by g of I, and it must be true for all positive integers m. If that is the case, so we just need to check it for one point, then we obtain actually a little bit weak version of the Bessenrodt-Ono inequality, because instead of the strong inequality we have the weak one for all x greater or equal than x0 and positive integers a and b. Actually, one can obtain here the strong inequality. In order to do that, it is enough to assume that x0 squared is greater than g of 2, and then we will obtain the strict inequality here. But it's not very important. We just dealt with the following inequality because it was more convenient for us somehow. So let me say a few words about the proof. The proof is actually very elementary, and the idea is very. It takes a few pages, but it's not. The idea is very elementary. So the first thing is to deal with the point x0. We want to just check the weak version of the Bessenrodt-Ono inequality for the x0. If we do that, then what we can do is to check the derivative of the following term. If the derivative is non-negative, then we know that we can conclude that this is non-negative. That this inequality holds for all x greater than or equal than x0. So this is just the idea, which is of course quite easy, but it's sufficient to prove the following criterion. So that would be nice if we could apply this criterion somewhere. So we wanted to do that, and we have the following. Let me denote this condition, which was nested in the criterion by star of n. And here we have the main theorem, actually maybe the second main theorem after the criterion. So now we consider a family of normalized sequences, GL of n, such that GL of n is bounded from above by n to the power l plus 1 and from below by n to the power l. And it must hold for all positive integer n. If that is the case, then we have the weak version of the Bessenrodt-Ono inequality for all positive integers a and b and x greater or equal than x0, where this x0 is just the value of GL of 2. And moreover, in order to have this inequality everywhere, we need to check a few we need to check the condition star n for some small values of n, namely depending on L. For instance, for L equals 1, we need to check it for all n between 1 and 8. Actually, for n equals 1, it's always satisfied, but for the sake of convenience, we write it in the following way. And it turns out that then we have this Bessenrodt-Ono inequality for all values of a and b and x greater or equal than x0. So where can we apply this theorem? Well, here is the following example. So now we can consider the function sigma d of k, which is the sum of diff powers of divisor of k. And in such a setting, we have the weak version of the Bessenrodt-Ono inequality for all positive integers n, a and b, and x greater or equal than 2 to the power d plus 1. So in particular, if d is equal to 1, then we obtain the sum of divisors. So we obtain that the first theorem I mentioned, that the family of polynomial corresponding to the partition function, we obtain that this is greater or equal than, we obtain the Bessenrodt-Ono inequality for all x greater or equal than 3. In the case of the plane partition function, we have sigma 2 of k, and we obtain that once again it is just like in the previous theorem, x must be greater or equal than 5. Another interesting example is the application of the criterion for the so-called polynomization of the over partition function. So for the over partition function, let me recall the definition of the partition function over partition function. So so in over partition function, the first occurrence of any positive integer may be overlined. So this is the difference between over partitions and partitions, and it turns out that for the corresponding sequence for the polynomization of the over partition function, it's sigma bar, which is defined by the following. So if we take 2 to the power m times L, where L is odd number, then it is 2 to the power m plus 1 times sigma of L. So in particular, if we can take 1, but let us observe that sigma bar of 1 is 2, so we cannot apply the theorem from the previous slide because the sequence is not normalized, but we can normalize it just by taking the sequence divided by 2. And if we do that, then we can apply the criterion and deduce the theorem of Lie from 2023 that which states that the polynomials associated for the over partition function fulfills the Bessenrodt-Ono inequality as well. And the last thing I would like to talk about is something which is worth pointing out regarding this theorem. Namely, let us observe that, of course, this theorem works for the partition function because sigma of n is bounded from below by n and from above by n squared. But if we fix some subset of positive integer a, then we have that the corresponding sigma a of n is usually not bounded from below by n, but by 1, and from above by sigma of n. Therefore, we cannot apply directly this theorem in that case. Therefore, we have decided to deal with that case separately, and what we were able to prove is the following. So we have this assumption as I mentioned, so G is between 1 and sigma n, and we have additional requirements hidden here. And then it turns out that we can once again have the Bessenrodt-Ono inequality for all x greater or equal than 3 if this inequality is from point 1 hold. Otherwise, we have just this the Bessenrodt-Ono inequality for x greater or equal than 4. Sorry. Yes, it's here. And in particular, one can apply it just to show that the polynomization, for instance, for k-regular partition function satisfies the Bessenrodt-Ono inequality for all positive integers m and n and x greater or equal than 3. So the k-regular partition function, so this k-regular partition function counts the number of partitions of n from where parts belong to the set of natural numbers without k, 2k, 3k, and so on. And at the end, let me just say a few words about the open problems. So the first open problem is devoted to going in a different direction. So here we wanted to find x sufficiently large in order to have the Bessenrodt-Ono inequality for all values of a and b. But now we can go the different way. We can go with x down and check whether the Bessenrodt-Ono inequality holds for all sufficiently large values of a, m, and n. And moreover, we can also investigate the log concavity property in the same direction, but it's much more intricate problem. And that's actually everything I have prepared for today. So thank you very much for your attention.
All right. Thank you very much for a very nice talk. Are there
Thank you.
any questions from our Zoom world?
Hello, Christian. Very nice
Hello.
talk. Yeah.
Thanks.
So, am I audible first of all?
Once again, could you repeat?
Yeah.
I can hear you
Am I
clearly.
audible?
Yeah.
Yeah. So, I have one question. First of all, how you obtained that recurrence relation in, say, fourth slide? I think that was in the fourth slide.
Okay, let me go back. You mean that one, the last one, right? Or
Yeah. This one.
so
All
both of this recurrence relation, the last one and the penultimate one, follows from taking the logarithm derivative of this generating function here. If you take the logarithm derivative with respect to x and then with respect to q, you obtain one of this recurrence relation. And if you do the symmetric thing, namely you take the derivative with respect to the logarithm derivative with respect to q and then with respect to x, then you obtain the second recurrence relation.
Okay. And that case of where you took a general set A, okay? So, did you try, say, taking, say, set of all primes? Okay. If you take set of all prime, we'll have, yeah, here. So,
Yeah, so
suppose we take set of all primes, then we'll have, instead of the divisor function, we'll have the function which counts the number of prime factors, right?
yeah,
And so if
probably.
that is the case, do we have some interesting results? I mean,
So in fact, I must admit that I didn't take a look on that special case, but it's very interesting because as you see on the next slide, for instance, so here is our main result for this a part, let's say for this partition function when a is a set, but we always assume that one is our set. In prime number settings, we do not have this requirement because then we will obtain also the family of polynomials where the degree will be usually smaller than n. Also, the leading coefficient will be different and there will be a lot of difference. So it's a bit more, it's of course very interesting, but it requires a little bit more different approach.
Okay. And one more question, just can I ask one more question? Yeah. So my last question is, so where you did it for general polynomial G, can you show that?
Yes.
Yeah. So in this case, what I wanted to ask is that suppose instead of GK being a divisor function, suppose we take some well-known arithmetic function, say Euler-Tauschen function or anything. So in how many cases we get interesting partition function?
Oh, that's also a very interesting question. So usually we obtain some kind of if we like it was mentioned before. So for instance, in this case, so for instance for this A partition, we obtain the sigma A function. So usually it is that kind of function, but I am not able to okay. So actually in such a setting we are able to always obtain that kind of function, sigma A of K function, but in a more
always
but
we
for
have this divisor kind of function, right? We always obtain this divisor kind of function.
Yes, exactly. But probably from some various partition statistic, from other partition statistic, we probably will obtain something different. That was the motivation for that work because we wanted to consider much wider family of polynomials.
Okay. I thank Krystian again for a very nice talk.
Thank you
And,
very
Okay,
much.
nice.